Question number 7. A sample of helium from a rock was found to contain two isotopes with the following composition by mass. Helium composition is given there. This is the percentage and this is the percentage, so we got two compositions of helium. Okay, state what is meant by the isotope. What are isotopes? Can anyone tell me what are isotopes?
Atoms with the same number of protons but different number of neutrons.
These are the atoms of the same element. Okay, these are the atoms of the same element which are having the same number of protons but different number of neutrons, or they have the same atomic number but different mass number. State what is the difference in the atomic structure of helium-3 and helium-4. What is the difference between these two? Helium-3 and helium-4.
So mass number.
Mass number is different, absolutely. And mass number is different because of what?
The number of neutrons.
Number of neutrons. Number of neutrons, absolutely right. Okay. So the number of neutrons are different in them, that's why the mass numbers are different. These two numbers are the mass numbers, okay, and they're different by neutrons. Different by neutrons only, okay, and they are the mass numbers. Okay, which isotope is used as the basis for relative atomic mass measurement? Which isotope is used the basis? The one which is having maximum percentage will be used the basis. Okay, so isotope 4 is being used as the basis because it has the maximum number of the maximum percentage here. Okay, this one is going to be used because it has a maximum percentage, max percentage. Okay, calculate the relative atomic mass of helium in the rock sample. Relative atomic mass calculation. So the mass given there times its percentage plus the mass given in the helium-4 times its percentage divided by 100, and we get the answer for that. And can somebody tell me what is the answer for that?
3.99008.
3.99008.
Yes, sir.
So we get 3.99. The answer should be very close to 4 because the percentage of 4 is 99%. Helium has the largest first ionization energy of the elements, of all the elements. State what is meant by the first ionization energy. First ionization energy.
Sir, the ionization energy of an element is the minimum amount of energy required to remove one electron from the outermost shell.
Okay, fine. But my definition is a little bit, standard basic one. 1 mole of a gaseous atom is converted into 1 mole of gaseous cation by the release of 1 mole of electron. The amount of energy involved at that time is called ionization enthalpy at S, T and P, standard temperature pressure. Okay, it's 1 mole of gaseous atom, 1 mole of gaseous atom is converted into 1 mole of gaseous cation by the release of 1 mole of electron. Okay, this energy is called ionization enthalpy. Okay, I'm not saying that your definition is not good. Your definition is good, but see, always do a definition which should give you maximum of that. Okay, now moving on to this part. Okay, state what is meant by the periodic property. What is a periodic property? What is a periodic property? Yes, please.
So the trends in a periodic table.
Do we have question number 8 here? Yes, we have question number 8 also. Before going into the periodic property, let us work on question number, yeah, we are left. Write an equation including states to represent the first ionization energy of helium. We have already written that one. Okay, so helium is He in the gaseous state, moving into He plus 1 charge plus 1 electron is released out, gaseous state. This is the first ionization. Explain why the first ionization energy of helium is larger than that of hydrogen. Now see the configuration of hydrogen. Hydrogen is 1s1 and helium is 1s2. To break a completely filled orbital, you need to give more energy. More energy is needed for it because it's a completely filled one. And hydrogen is partially filled. Okay? Moving on to the first ionization energies of boron are given to you. Okay? First, second, third, fourth, and fifth. Now, let us do the configuration of boron. What is the configuration of boron? Where is boron? 1s2,
Group 3.
2s2, 3p, 1. Right? Okay. If I'm drawing this graph for it, keep in mind how many shells you can see here in it? 3 shells you can see in it. So how many jumps of ionizations are possible? 2. So the graph will tell us a story that there is a big jump, then straight, then a big jump, then straight. So this jump and this jump, these are the jumps between the shells. Okay? Shell number 1, shell number 3, shell number 2, and shell number 2 and 1. So when you see 2 big jumps, you will jumps plus 1 will give you the number of shells. So 2 plus 1 will give you 3. So there are 3 shells in it. Okay, now when you see the ionization energy is given to you, so what will you do with those ionization energies? See the ionization energies now. The first ionization energy you can see. Second ionization energy is almost how much? 3 times. Then third ionization energy. Then if you can focus, this one is very, very big one. A very big jump. Are you with me, everyone?
Yes,
Yes,
sir.
sir.
Okay, so when we see that there is a very big jump in the ionization energies, first 5 ionization energy, what is the atomic number of boron? 5. Okay, give me a minute and let me explain that to you now. Okay, so 1s2, 2s2, 2p. This is 2p1, I guess, right? For boron, 5 electrons are there. Now, let us work on the ionization energies of boron. These 3 electrons are to be eliminated from the second shell. So you can see 2p you are eliminating 1 electron, then from 2p to 2s, I told you there will be a big jump, but that big jump will not be bigger as compared to the jump of the shell. It's a little bit bigger. See this and these two. They are different by around like 3 times, multiplied by 3, and this is around multiplied by 5. Okay? But what about this one? This is a very big jump. The approximation is that if there is another shell starting, then the jump should be 10 times greater than the first one. Maximum it can go like that. Okay? But this jump is, if I multiply 10 here, 801 times 10, so I'll get 8000. But this is much more than this. Maximum you can go to any limitation. So a very big jump is there. Right? So it means there is a shell changing. Okay, one jump you can see here, a big jump. So one jump plus one, two shells are there. And then we have the electron. This will go from 1s2, and this will be the last electron from it.
So again, screen share again, sir.
See?
So again, screen share again. Is sir, your screen share is glitched.
On my screen too.
It's fine now?
Yes, sir. Now it's fine.
Okay. I'm repeating once again. Okay. What I'm saying is the electronic configuration of boron, you need to do that. Okay. And how you're going to do that? This is 1s1, 1s2, right? This is then 2s1 and 2s2, and this is 2p1. So eliminating first electron, then eliminating a second electron from 2s, then the third electron, first electron, then eliminating first from 2s, second from 2s, then eliminating first from 1s and second from 1s, right? So we are touching here 2p, then you can see difference is there, big difference, 3 times, around 5 times. So this is a subshell area. From one subshell, and from 2p to 2s you're moving. Okay? But when you see there's a big jump, where's the big jump? Yeah, here. Then you're moving actually from shell to another shell, from energy level to another energy level. Then again, between these two, 25,000 and 32,000, the small difference is there between these two. They're already in thousands. So it means that you are in the same orbital. Are we clear with this?
Yes, sir.
Yes,
Now
sir.
let us move to the questions now. That was only an explanation to you. Now the question. What is the question saying? Question says state and justify the group in the periodic table in which boron is placed. So boron is in which group of the periodic table? S, P, D or F? So the configuration is telling us 1s2, 1s2, 2s2, 2p1. So it is in the p orbital or p block. The configuration end up on p, so it's a p block element. Right?
Yes.
Okay.
Yes, sir.
Which of the following represent the second ionization energy of boron? Okay, second ionization energy of boron is Okay. Is this the second ionization energy of boron? The first one?
No, sir.
Is it the second one?
Yes, sir, the second one.
Okay. First of all, ionization energy is an endothermic process, so you are going to choose the endothermic ones. Either it will be the first one or the second one. Okay, it cannot be exothermic. Alas. Now, why it is the second one? Why not the first one? Because the second one is giving you the overall ionization energy. Overall means first plus second. Okay, and part B is giving you one electron, any plus one charge is there, it's moving to 2 plus, gaseous states are mentioned there, the electron loss is also mentioned here, and it's an endothermic also. So this is option B, right?